Good morning everyone. My name is Mrudula, working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. Today I am going to discuss about different types of compensations which are being used to improve the power factor from the subject called Industrial Electrical Systems. These are the contents which I am going to discuss today. The first one is the power factor correction methods. As I said in the previous lecture, that is, the power factor should be almost equal to unity. Then only the cost reduces, the electricity bill reduces, as well as the losses reduces and damage also reduces. So in order to make the power factor to unity or 1, we use different types of compensators. In these compensators, we will be using mostly the capacitors as compensator, which is being connected in parallel to the load. So what are the different types of correction methods? The first type of correction method is the SVC, that is static wear compensator. The second one is fixed capacitors. The third one is switch capacitors. The next one is synchronous condensers, and the next one is static wear compensator, which is also called as StatCom, static synchronous compensator. The last one is modulated power filter capacitor compensator. So here you can see 6 different types of compensators in order to improve the power factor. The first one is static wear compensator, that is SVC. The SVC is a shunt device. Shunt is nothing but which is connected in parallel. So as I said, the capacitors are being connected in parallel to the load. So this is also called as a shunted device of FACS, that is flexible AC transmission system. Like in flexible AC transmission system, we will be connecting this SVC in parallel. So it is also called as a shunt device by using the power electronics to control the power flow. That means we will be using the capacitors, and in addition to the capacitors, we will be connecting different types of power electronic devices also. That may be a diode or a thyristor or an IGBT, or based on the load. We will be connecting different types of power electronic devices which are used for controlling the power flow through the capacitor and improve the transient stability of the power grids. And to improve the transient stability of the power grids, we will be connecting this SVC, that is static wear compensator. The SVC regulates the voltage and at its terminals by controlling the amount of reactive power injected into the or absorbed from the power system. That means the SVC regulates the reactive power which is being injected. And when the system voltage is low, the SVC generates the reactive power, that is SVC capacitive. And when the system voltage is high, it absorbs the reactive power which is inductive. That means in both the ways it is being used. When the voltage is less, it is used as a capacitor, and when the voltage is high, it absorbs the reactive power and it behaves like an inductive. So in both the cases we will be using, that is when the voltage is high as well as in voltage is low, the SVC technique is being used. The variation of reactive power the variation of reactive power is being performed by switching the three-phase capacitor banks. That means if the input supply is single phase, we will be using the single phase capacitor bank, and if it is a three-phase supply, we will be using the three-phase capacitor banks. And the inductive banks are being connected on the secondary side of the coupling transformer. Means a coupling transformer will be there where you have the primary as well as secondary in the transformer, and we will be connecting these three-phase capacitor banks to the secondary side of the transformer. Each capacitor bank is being switched on or off. That means the controlling is in our hand to whether switch on or switch off the capacitor, and these switching are being used by three thyristor switches. That means we will be using the thyristors in order to control as well as in order to switch on or switch off the capacitor banks. And this is called as thyristor switched capacitor, that is TSC. And reactors are either switched on or off. The reactors are being switched on or off using the thyristors again. Thyristor switched reactors, you will call that one as TSR, or phase control thyristor controlled reactor TCR. That means you can control the capacitor banks as well as you can switch on or off the reactors also. So the first one you will call it as TSC, that is thyristor switch capacitor, and the second one you will call it as TSR, that is thyristor switch reactor, in order to control the reactor. A rapidly operating static wear compensator can continuously provide the reactive power required to the control dynamic voltage swings under various system conditions and thereby improve the power factor, transmission as well as the distribution performance. That is, in order to increase the transmission as well as distribution performance or the efficiency of the whole system, we will be using this SVM technique to provide the reactive power which is being required based on the voltage swings. That means there will be voltage sag as well as swell. The voltage also varies. This variable voltage, because of this, harmonics will be created, and this harmonics will affect the power factor and will increase the reactive power. So in order to compensate all these things, we will be using the SVC technique. By installing an SVC at one or more suitable points, we can place this SVC in different one or more number of points in a network. It will increase the transfer capability through the enhanced voltage in order to improve the enhanced stability, voltage stability, while maintaining a smooth voltage profile under different network conditions. That means at different network conditions also we can maintain the voltage in a smooth manner, that is in a stable manner without any harmonics. And SVC can mitigate the active power oscillations. Means the active power will be changing based on the inductive loads. So this oscillations can also be controlled or mitigated or reduced by using the SVC. Second type of compensator is fixed capacitor. The first type was SVC, the second type is fixed capacitor, where the load does not change. Means where the load does not change. That means for fixed load or where the capacitor is switched with the load. Such type of load side of ideally suited for power factor correction. That means this type of capacitor is being used where the load does not change. That means for fixed load, we will be connecting this fixed capacitor. When the load is connected, the capacitor will be switched on. When the load is not connected, it will be switched off. But there will be no variation in the load. It is in the on condition or is in the off condition. And each fixed capacitor bank is being designed for high reliability and long life. These products are being designed for applications that do not contain the harmonic generation. The third type is switched capacitor. The first type is SVC, second one is fixed capacitor, the third one is switched capacitor. It is mostly suited for centralized power factor correction. It is mostly suited for centralized power factor correction in applications where the plant loading is constantly changing. That means where the plant loading will be constantly changing, the load across the load which is connected to a particular plant will be always in a frequently changing manner. To that particular case, we will be connecting this switched capacitor, resulting in the need for varying amount of reactive power. That means as the load will be frequently changing, we need to connect a varying amount of reactive power to it. So, an advanced microprocessor based, here we will be using an advanced microprocessor based reactive power controller, and which measures the plant power factor via a single remote current transformer. By using a single remote current transformer, we will be calculating the plant power factor and switches the capacitor modules on or off will be done based on the power factor which is being measured by a remote current transformer. So typically this is being applied at service entrance or near the fluctuating loads. That means for fixed load, we will be connecting the fixed capacitor. For variable loads, we will be connecting the switched capacitors near the plant. The next type is synchronous condenser. Synchronous condenser is a salient pole synchronous generator. It is a salient pole synchronous generator without a prime mover. That means we don't require any kind of prime mover for this. Synchronous condenser stabilizes the power system voltage by supplying the reactive power to the power system and used for power factor correction. It is more economical than the capacitors. That means instead of capacitors, we will be using here a synchronous generator, synchronous condenser, which stabilizes the power factor. Next type is STATCOM, that is static synchronous compensator. The STATCOM is a shunt device. Shunt is, I said, parallel. Shunt device of the FACS system, that is flexible AC transmission system. By using a power electronics, for controlling the purpose and in order to improve the transient stability of the power grids. The STATCOM regulates the voltage and it terminates the controlling it at the terminal. That means at the terminal we will be connecting the STATCOM and it controls the amount of reactive power injected into or absorbed from the power system. When the system voltage is low, STATCOM generates reactive power. That is STATCOM capacitive. It becomes a capacitive thing. So this is another type of compensation where system voltage is high. That means when the system voltage is high, it absorbs the reactive power similar to the SVC. STATCOM can also provide instantaneous and continuously variable reactive power in response to the grid voltage transients. That means if the grid voltage is being changed frequently, based on the grid voltage, the STATCOM can compensate. So initially STATCOM at installing the STATCOM at one or more suitable points. That means the STATCOM can be placed in one or more number of points in a network in order to increase the grid transfer capability. Through enhanced voltage stability while maintaining a smooth voltage profile under different network conditions. The STATCOM provides additional versatility in terms of power quality improvement capabilities. The determination of capacitor value. How to determine the capacitor value? That means here you can take an example where the power factor is 74%, that is 0.74, and the active power, the actual power, you can say it as actual power, is around 594 watts. So the power factor is being now boosted to 0.97. That means in order to boost the power factor to 0.97, you have to change the reactive power, that is kVAR value, as the power factor formula is kW by kVA. This is the apparent power and this is the active power. So by changing the reactive power, the kVA value will change. So by changing the kVA value, you can change the power factor value also. So in this manner, we can calculate the capacitor value also. Power factor measurement. The power factor can be measured by using the power factor meter, which is also known in the power industry, which is mostly used in the power industry. The power factor can also be calculated by installing a watt meter along with the ampere meter as well as the voltmeter. Means in addition to the voltmeter and the ammeter, we will be connecting a wattmeter in order to measure the power factor. So here the power factor is equal to active power by apparent power. So this is one of the example for the power factor measurement. This is nothing but the active. This is nothing but the apparent. Here you can see a wattmeter which is being connected. This is your ammeter, and based on the wattmeter reading, here you have wattmeter reading as 1.5 kilowatts and the ammeter reading is 9.615 RMS. So S is equal to, based on the formula, I into E, that is 9.6. This E is nothing but your EMF, that is nothing but your voltage. So your voltage into current value will give you the S value, that is the apparent power. So the apparent power formula is voltage into current. You will be getting the apparent power, and the active power is being measured by using the wattmeter. So by ratio of these two will give you the power factor value, that is 0.65. So in this manner, by using a wattmeter, we can calculate the power factor value in a particular network. What are the advantages of power factor correction? It can eliminate the power factor penalties and it can increase the system capacity and it can reduce the losses in the distribution system and conserve energy. Energy can be conserved, that means energy can be saved, and improve the voltage stability, increase the equipment lifespan and save on utility cost, and enhance the equipment operation to improve the voltage, it improves the energy efficiency, it reduces the size of the transformers, cables and switchgear elements or different components which are used for the switchgear. Next one is delay costly upgrades, less total plant kVA for same kilowatt power consumption, and improves the voltage regulation due to the reduced line voltage drop. So these are the different advantages of power factor correction. Power cost reduction can also be done, that is the kilowatt demand with a trigger point typically between 85 to 95% kVA demand can be increased, the kVAR can be reduced, and the savings of the utility company derives reduced generation, transmission as well as distribution costs are also being reduced by improving the power factor. System capacity increases. The overall system capacity also increases by improving the power factor. Voltage improvement as well as power loss reduction also can be done. What are the disadvantages of low power factor? Previously we have seen the advantages. Now these are the disadvantages of low power factor. What are the disadvantages? It increases the heating losses in the transformer. It reduces the plant lifespan and it unstabilizes the voltage levels. The voltage levels will be fluctuating. It increases the power losses. It upgrades costly equipments. It decreases the energy efficiency. It increases the electricity cost by paying the power factor surcharges. So these are the different disadvantages of low power factor. So power factor has to be improved or increased, or it should be almost equal to 1 or unit. By observing all these aspects, the power factor should be almost equal to unity and should be improved by using different kinds of techniques, like it may be SVC or it may be a STATCOM or it may be a fixed capacitor or switched capacitor based on capacity of load or based on location to be placed. So based on the location and based on the load, different types of switching devices or different types of compensators are being used. In next class, I would like to discuss about the PCC. Thank you.